So everyone knows what is the concept of inverse. Inverse. So we consider maps between two spaces. So here the two spaces are finite dimensional spaces, and we consider maps are linear. Maps are linear. So therefore life is simple when we have a linear map, because every linear map f between two finite dimensional spaces with respect to certain ordered basis, we can represent the function in terms of a matrix. So f can be represented in terms of a matrix A. So at present, assuming that these two spaces of are having same dimensions, so therefore we will be getting a matrix of order n by n. So we are having a square matrix. We are having a square matrices. So in general, it is not necessary. So by using the, suppose if I start with an element x, so we have ax. So is it possible to come back so to the same element what we started with? So there comes a concept of inverse. So by using the rank nullity theorem, in order to check the whether the matrix is invertible or not, A inverse exists or not, so we can check whether it is 1 1, because if it null space of A is singleton, only 0 goes to 0. And as we consider a linear map between two equal dimensional spaces, so therefore by rank nullity theorem, this itself is characterizing the invertibility of a matrix. So therefore, as we consider a square matrix, so A inverse exists if and only if the null space of A is singleton at 0. So when we start with any element x, so we can have Ax. When we apply A inverse A, then we can come back to x. We can come back to x. Therefore, this inverse we can talk about when we have a square matrix. But most of the time it doesn't happen. Suppose we have a system of linear equation. So let me take Ax is equal to B when A is a square matrix. And this system is solvable or not. So when we consider the corresponding range space of A, if it is full, then every element B in the range space of A, the system is solvable. So when it is solvable, then the question comes whether we get a unique solution or no solution, whether we get a solution or no solution. So first, whether the system is solvable or not solvable, no solution. If it is a solution, if it has a solution, then there are two parts, whether we get a unique solution or infinitely many solution. Unique solution or infinitely many solution. So here comes the problem. If there is a unique solution or no solution. So now for unique solution, then the concept of invertibility is useful. So therefore, how to get the unique solution for that system? So for this system, what is the unique solution? Unique solution is nothing but A inverse B, if it is invertible. So we get X. We know the solution that is unique because A inverse is unique. Therefore, A inverse B is a solution which is X. But most of the times it may not happen. Though it has a square matrix, if A is a square matrix, sometimes it has no solution. If no solution, which means that B is not a member in the range space of A. So the columns of A may not span the entire, therefore B may not lie in the range space of A. So range space is nothing but the space generated by the columns of A. Okay, so if there is no solution, then we should find out some solution. We cannot say solution, we can find something which is close to the solution. So we have issues when we have no solution. And we have some issues when we have infinitely many solutions. Suppose A is not necessarily square, which is a rectangular, purely rectangular. Suppose there are infinitely many solutions. Infinitely many solutions. Then the question comes, which one should be taken? Which one we need to get back X what we started with. Therefore, there are issues when there are no solutions, there are infinitely many solutions. So therefore, we will not be able to talk about when the determinant of A, this is not the way in general, but I'm writing determinant of A is 0, then we have issues. So for that, and then if A is a purely rectangular matrix, then we would like to have some kind of inverse. Okay, so the concept of the general inverse of a matrix, square matrices, is generalized to a different settings. So for any matrix of any order. Therefore, we are starting with the matrix of order m by n. So Moore-Penrose inverse equations. There are four equations. There are four equations. We call MP1 Moore-Penrose equation 1, 2, 3, 4. Suppose we will be proving it. So shortly, now I will be explaining this. So for every given matrix A, always we get X. Always we get X, which is unique. Which is unique, which will satisfy these four equations. So such matrix is called Moore-Penrose inverse of A. This is a kind of inverse which is denoted by A dagger. Therefore, one can, this is a generalized notion of a square matrix. If A is a square matrix, a general inverse exists, then all four equations are satisfied. We can say beyond, we can say for any rectangular matrix, always such X exists, which is unique and which will satisfy all four equations. Okay, quickly we will see what are the implications of each equation. So we denote the symbol A of 1 is nothing but the 1 inverse of A, which means that the matrices which satisfy the first equation, Ax, A is equal to A. So if matrices satisfy the second equation, then we write it as A of 2, which is the collection of all two inverses. We simply say it is one inverse. If the first equation is satisfied, the second equation satisfied, then we say two inverse, then it goes on. Therefore, one can ask, so one can have so many matrices which are one inverses. When you put expecting the two conditions are required, then the collection becomes smaller. Then we have the collection of 1, 2 inverses. Then we are expecting all three conditions are required. Then we have the collection which is still smaller. Then we are expecting a matrix satisfying all the four equations. So that is the smallest. So even in fact that is a singleton set. Therefore, our A dagger, what we are saying, it is a member over here. So we have so many matrices satisfying the first equation. But if we are expecting a matrix satisfying all the four equations, which that particular matrix is denoted by this symbol A dagger. And then there are several other possible chains are there, then we are not going to in detail. Okay. Now quickly we'll see what is a 1 inverse. So as I said, 1 inverse satisfying this. The advantage of this relation, it gives, this particular relation gives two projections. So therefore we have two idempotent matrices. So I'm not saying orthogonal projection, it is just a projection in a general term. Otherwise you can call idempotent, which is P square is P. So we have the matrix AG and GA, which is a projection, these two matrices are projections, A of G and G of A. If we have a 1 inverse, we get two projections. When we square them, then we get the same matrix. So therefore, these two matrices will help us to decompose the spaces. Every projection, every idempotent will help us to decompose a space. So this happens. And when we have one solution, one inverse, we want to check whether the system is solvable or not, whether the particular B in range of A or not, whether it is there or not, then we can check the condition. If we know one inverse, if I know one G, which is G inverse, then we can check this condition. So this condition is simple. So there are several ways to construct this G depending on your A by knowing the rank. And then this simple equation is helpful to see whether the system is solvable or not, whether the system has a solution or not. If I know one solution, Z, or if I know one G, which is one inverse, this G, then we can get every other solution. Therefore, every solution is of this form. Therefore, the matrix satisfying the first relation is called equation solver. Therefore, we have many equation solvers. So among which we want to find out a solution which is good in some sense, so that we will be imposing next conditions. Therefore, two inverses is nothing but the mere just a reflection that we can say some kind of relation with the one inverse. But there are issues when we try to find G. So here when we are trying to find G, even if you have a 2 by 2 matrix, you start with any arbitrary G, we will not be getting linear equations. So we will have a non-linear equations. Therefore, finding two inverse is not easy. Okay, so now when we combine these two, then this is called 1-2 inverse. So which means the matrices G satisfy the first two equations, these two equations. So they are called 1-2 inverses. And there are so many results. One can have an association with respect to rank. One can check if one inverse is there and rank condition, whether it could be a 2 inverse also. So this is a small exercise one can go. If I start with any one inverse, if I check the rank of the matrix, given matrix A, and rank of that one inverse are same, then this matrix will automatically satisfy the second equation. Therefore, this is 1-2 inverse. So we have seen one inverse is nothing but equation solvable, solver net. And if I have 1-3 inverse, so here we have an issue. Already I said there are two issues. If there are infinitely many solution or no solution. Now let us discuss with the no solution case. If there is no solution, then we want to find out a solution which is nearer. Therefore, we have a range space over. So our solution, our AX collection of all AX here, but B is outside because B does not belong to range of A. In that case, we will be choosing an element. We will be choosing an element in the range space. So that is nearest. So that particular solution is called least square solution. So therefore, least square solution is a solution. It is not a solution actually. It is not a solution, but which is nearest, which is an element in range of B, but with the corresponding x naught if I apply, but which is from B. So there is a connection between 1 and 3 inverse with this. Therefore, if anyone knows 1, 3 inverse, let us say B, G, then one can find GB. The GB is always a least square solution. Therefore, what I'm summarizing, so I will not be explaining all the results. If somebody knows 1, 3 inverse, then simply calculating GB, it will be the least square solution. Remember, this least square solution is not necessarily unique. There could be many least square solution. When it is unique, then we have a last result. The last result says rank of A is n, then we have a unique least square solution. Therefore, 1, 3 has an association with the least square solution. These are the characterization for a unique least square solution. So one can easily verify this all conditions are equivalent. If the system has a least square solution, then the rank of A is n, because the rank of the given matrix is of size m by n. So and A has full column rank. And next, finally, we'll see 1-4 inverse. 1-4 inverse, because here we have seen another set of issue is infinitely many solution. If there are infinitely many solution, which one should be chosen? So we want to choose a solution which is near the origin. So nearest to the point origin. Therefore, that solution is called minimum norm solution. Therefore, minimum norm solution, among all possible solutions, we have too many solutions. So among which we can find a one which is nearest the origin, nearest from the origin. Therefore, when we know 1-4 inverse, as I said earlier, so last time we had the least square solution. This time we have the unique solution of minimal norm. So now combining all of them, now you will be in a position to tell what can we expect on A dagger. A dagger is a matrix satisfying all the four conditions. Therefore, one can expect this A dagger will give a unique least square solution of minimal norm. So that is the concept of A dagger. So A dagger exists for any matrix. So that will give the least square. So there are several ways one can find the Moore-Penrose inverse of any matrix. In general, a lot of difficulty is there to find Moore-Penrose inverse, and people are writing codes to use some programming to find out the Moore-Penrose inverse of some matrix. If the size of the matrix is too much, then it is very difficult to find. But there are some simple results where one can find the Moore-Penrose inverse of this. If a matrix has a full column rank or full row rank, we have an explicit formula to calculate the Moore-Penrose inverse. So that is given over here. So we will be finding f star f f star f. F star is nothing but the conjugate transpose, and f star f will be invertible, and we find its inverse. Then we can find the Moore-Penrose inverse. Therefore, finding Moore-Penrose inverse of a full row rank matrix or full column rank matrix, it is slightly easier. And we know very well any matrix A with a certain rank, which can be factorized as a product of two matrices. Each matrix will have certain rank. Therefore, if we are able to use the full factorization of a matrix, then we will be finding the corresponding Moore-Penrose inverse just by taking the Moore-Penrose inverses of the corresponding matrices, but in the different order. This is also possible, but it is time consuming. So we need to know G star. First of all, we need to know the factorization, then G star and F star F, then finding inverse, then finding inverse of another matrix, then finding the product. So it takes its own time. And there is a simple equivalent definition of a Moore-Penrose inverse. This definition is helpful to, you can imagine in terms of for an operator. So we have a null space over here, and we have a range space. And when we have a map A from x to y, so when we restrict the map, because a null space of f is singleton at 0, no issue. If there are non-zero elements which are going to be 0, the map is not invertible. Therefore, we will be restricting the map into its complement. So it is n of a perp. Therefore, n of a and n of a perp are, if you find the orthogonal direct sum, it will be full. Therefore, when we restrict this map is invertible. It is inverse exist. Then you can talk about this map from the space to range of A. It is 1, 1 and not 2. Therefore, motivation from this, one can have many results. If you find the double dagger of A, then you will have A. And then when you have A star A dagger, then you will have this expression. These are all some properties of the Moore-Penrose inverse. So this concept was independently analyzed by two mathematicians, Moore and Penrose. So the definitions were given independently in 1935 and 1955. And mathematician did not use the proper notations. They used some telegraphic symbol kind of notations. People did not understand. And this is a simple definition one can easily understand. For any matrix, always A dagger which goes from range of A to range of A star. Therefore, you get two projections. You get one on range of A, one on range of A star. So this definition is helpful to define the Moore-Penrose inverse of a bounded operator between two Hilbert spaces. For my convenience, so I'm restricting my operator T from H to H, where H is any Hilbert space. So T is bounded. T is a bounded linear operator. So the image of the unit ball is bounded. So for any T, always we can talk about T dagger. T dagger exists, there is no issue. But T dagger may not be bounded in general. T dagger always exists, there is no issue. So the T dagger is unique always. And T dagger is densely defined. density defined. But when we have range of T, range of the operator which is closed, then we can expect the boundedness on T dagger. So this is a simple characterization for boundedness of T. And this notion is extended to many settings, and from bounded to unbounded, and then for different class of operators, for closed operators, especially closed operators. So we have published some works related to the Morpindo's inverse of unbounded closable operators. So closable operators are operators which are having closed extensions. What do you mean by closed extension? It has an operator T. There is an operator S which is closed, and T has an extension. T has an extension. Then we say that T is closable. T is closable. So therefore, every closed operator is closable because that operator itself is closed. Therefore, the collection of all closable operators is bigger than collection of all closed operators, where the Morpindo's inverse concept was not defined. So we define the concept of Morpindo's inverse in unbounded closable operator settings, and we analyze the Cartesian product for closed operators, which got published in Linear and Multilinear Algebra in 2025. So now there are some aspects about inverse. So now, as I said, the title of my talk related to inverse, particularly Morpindo's inverse. In short, we write MP inverse. And this relation is known to us. This is called reverse order law. When we want to find the inverse of the product, which is the product of the corresponding inverses. So this is called reverse order law. This holds good for regular matrix inverse. But in general, this is not true for Morpindo's inverse. And we have found several characterizations. So already so many characterizations are plenty of characterizations are available for matrices. And then we have done some characterization for bounded operators between two Hilbert spaces. So that got published in this journal. This is related to the product. So what we are going to see some outline about the Morpindo's inverse, about the sum. So what is the sum? If I have the two matrices, I know they are invertible, A inverse, B inverse exists. I would like to know whether A plus B is invertible or not, whether inverse exists or not. But in general, that is not true. For example, you can take A is an identity matrix, so B is a minus I. Here both are invertible, but when you find the sum, which is a zero matrix, which is not invertible. Therefore, this result is not true even for a regular inverse, even for a regular inverse. So there are so many characterization available for regular inverse, and one can also split the A inverse plus B inverse of this form, A inverse plus B inverse of this form. Then one can find the A inverse plus B inverse nicely. So this relation is useful. And then there are so many results available in literature to go for the inverses, to go for this inverses. And motivated by the work of this general inverse, and people started working to find the Morpindo's inverse, the sum for any matrices. So A and B are given matrices. As I said, for any matrix, we know the Morpindo's inverse. Therefore, A dagger, B dagger also both exist. So now we have to know whether this relation is same or not. But as I said earlier, this is not true. This is not true. So people started finding some several characterization about when this relation holds good. And you have several sufficient conditions for this. So one of the sufficient condition I'll simply write. So if I have A B star is equal to 0 and B star A is equal to 0, then we can expect this relation to be true. This relation is true. So therefore, when we have these two conditions, so automatically we will be having, so now we are expecting, remember this commutative property is not true. Therefore, we need two conditions. Whereas in general, the matrices, the commutative property is not true. So A B dagger is not necessarily the same as B dagger A. So, but we are expecting these two products are zero, then we can have this conclusion. Then people started finding the necessary and sufficient conditions for Morph-Penrose inverse and whether the sum is true or not. They started defining many order relation. Order relation. So one of the order relations I like to write. So M, A, B are two matrices. If I say A less than or equal to B, A less than or equal to B, this is one set of order relation, and we have A dagger, B is equal to B, A dagger A, which is equal to A, B dagger A, which is equal to A. So now it looks strange for you. So how one can have this relation, how this relation satisfying all other partial ordering and so many other things. But people started working to write the conditions in terms of order relations, and then they are proving. So the results are generated in terms of order relation. So we will come to know from the order relation which is before us, or which matrix is behind which other matrix. If all other matrices can be comparable in this fashion, then with respect to the particular order, we will be able to say whether the sum of Morph-Penrose inverse is Morph-Penrose inverses of the sum. So therefore, finding Morph-Penrose inverse is not easy, as I said earlier. So where is this useful? Suppose if for a given matrix C, if we are able to decompose C as A plus B, this decomposition can happen in many ways, but we will choose one of the decompositions A and B so that A dagger is easy to find and B dagger is easy to find. Then in order to find the Morph-Penrose inverse of C dagger, and assuming that this relation is true for that particular matrices A and B, therefore A dagger plus B dagger is equal to A plus B whole dagger. Therefore, it is easy to find. So we will be adding the corresponding Morph-Penrose inverses. The same thing one can also think about for a product. Suppose we have a matrix C, we want to know C dagger. What is C dagger? Suppose this matrix is.
Sam sir?
Yes, sir.
Sorry, we have just 5 more minutes.
Yes, sir.
Yeah,
I'll finish in, sir, in 1 minute. Yes, sir.
Yeah.
Yes. Thank you, sir. So we have a factorization of a particular matrix AB. So as I said, a necessary sufficient condition for the reverse order law is verified, then we will be able to find the Morph-Penrose inverse of C dagger easily by taking the product of B dagger and A dagger. In the same fashion, one can think about for the sum. One can think about for the sum. So with respect to the basic ideas on the sum, one can also work in this direction. There are so many open problems, and then some good set of results are there for matrices. So if you have good foundations on operator settings and unbounded operator settings, so you must be in a position to extend many of the results to for a general class of operators. So with this outline, I would like to wind up. I would like to stop.
Thank you, sir, for the wonderful talk. We have time for few questions. Anyone have any question? So I have a question. So let's say we have a rectangular matrix and we talk about its singular values. What is the connection to the Morph-Penrose inverse singular values? Is there any connection between that of A and A dagger?
Yes, sir. For we know the singular value decomposition, so we will be factorizing with respect to the diagonal UV. So here for this is A, this is A. So therefore, if we find it's A dagger, then we will be finding the corresponding matrix in the reverse order V, this dagger and U, because there the finding of this corresponding diagonal, in the middle we have the matrix. So finding the inverse is easy, because for a diagonal matrix we can find the Moore-Penrose inverse easily. So if we are having the singular value decomposition of the matrix, then one can easily find the Moore-Penrose inverse. Yes.
But these inverses, I mean, the singular values need not be inverses of each other. Although as a matrix, the inverse, Moore-Penrose inverse holds, these singular values need not be, I mean, 1 by sigma 1, for example. That need not be the case, right?
That will be the case, sir. Actually, the sigma, what I'm saying is, when we keep all the non-zero diagonal entries above, and then we are keeping the zero diagonal entries at the bottom, then the inverse of sigma will be the inverse of the diagonal entries. But wherever zero, then we can keep the entries as it is. So now we will not be changing. That becomes the inverse of it. So here what that becomes the inverse of the sigma, the matrix sigma.
Oh.
Yes, sir. Yes.
Any more questions? Not, let's thank the speaker once again. Thank you, Shanthan. Thanks for the nice talk.
And thank you, sir. Thank you to you for giving me an opportunity to present my results. General results. I have not presented any of my talks. Yes, sir.
We have 5 minutes break, and at 11:10 we can continue the next session.
Thank you all. Bye.
Thank you, sir.
Let us ask Dr. Sandeep here for James. There is an announcement. If any one of you want attendance, please wait. Actually, yes.